Chapter 2, Limits, 2.6, Continuity, Part 1. The graph on the left represents the length of a fish T years after it is hatched. The graph on the right represents cost of metered parking, where only quarters are accepted and each quarter buys 15 minutes of parking. You can see that the graph on the left is a smooth line. The graph on the right is made up of line segments with gaps in between the lines. This brings about the idea of continuity. A function is continuous on an open interval if it has no breaks or holes on that open interval. For the graph on the left, it is continuous for all values of t greater than 0. On the right, there are places where the function is continuous, but there are also a lot of discontinuities. There's a discontinuity at 15, and at 30, and at 45, and 60, and so on. So the one on the right has sections in which it is continuous, but definite points of discontinuity. A function is continuous on an open interval if it is continuous at every point on the interval. That's the formal definition of continuity. So, if a function is continuous on an open interval, if it is continuous at every point on the interval, the question becomes, what does it mean for a function to be continuous at a point? Well, what it means is that the limit of the function as x reaches that value a is equal to f of a. So a function f is continuous at a if the limit as x gets close to a of the function is equal to the actual value of the function at a. This really says three things. First of all, it says that the point x equals a is in the domain of the function f. It also says that the limit as x approaches a, that limit exists. And then lastly, it says that the function evaluation at a is the same as the limit. This is called the continuity checklist because it is a good way to determine if a function is continuous at a point. Let's do an example. Let's use the continuity checklist to determine if this piecewise function is continuous at 2. Okay, we have to check three things. Is the point 2 in the domain? Does the limit exist? And is the limit the same as the evaluation? So we'll start with the first one. The point x equals 2 is in the domain of the function. In fact, if x equals 2, the function is defined by x squared plus 2x. And so f of 2 is 2 squared plus 2 times 2 is equal to 8. All right, let's go on to the second check. Does the limit exist? Well, let's check it. Let's look at the limit coming from the right and from the left and check that they are the same thing. Coming from the right, if x is bigger than 2, then f values are calculated by x squared plus 2x. So coming from the right, the limit is equal to 8. What about coming from the left? Coming from the left, then x is less than 2. And when x is less than 2, the f values are calculated by 3x. So coming from the left, the function takes on the value of 6. Coming from the right, the limit is 8. Coming from the left, the limit is 6. Since the two limits do not agree, the left-hand limit and the right-hand limit do not agree, we say that the limit does not exist. And in fact, you can see that coming from the left and coming from the right, I reach two different heights. So, the second criteria is not fulfilled, and f is therefore not continuous at the point x equals 2. We don't even bother checking the third criteria. Once you know that it's not continuous at a point, that it doesn't fulfill one of the requirements, you stop right there. All right, I'll see you in part 2 where we continue this discussion.